Hi everyone. Today we're going to be talking about a logarithmic identity, and it's called the change of base identity. Let me tell you what it states. It says that for all b, c, and x that are positive reals, it is true that log b of x can be decomposed in the following way as log c of x divided by log c of b. This is quite a useful identity because it allows you to change what the base is into something else, which is from b into c. That can be helpful in simplifying expressions. And I'll show you a few examples of how this is useful after we prove this identity. So let's go ahead with proving it. The main idea is to exploit the fact that logarithms are equivalent to exponents. So we will use exponent laws. First, we have to convert our logarithms, this one, and this one, into exponents. So what we'll do is we'll let p equal to log b of x, so that equivalently we can say that b to the power of p is equal to x. We're going to let q equal to log c of x, so that equivalently we can say that c to the power of q is equal to x. And finally we're going to say that r is equal to log c of b, so that equivalently we can say that c to the power of r is equal to b. So as you can see, we've turned these all into exponential equations, and what we really want to prove is this over here, which is the same as saying p equals to q over r. And just to get rid of the denominator, we're going to try to prove that rp is equal to q. So let's go ahead and try proving that. There's a trick that we're going to use, and the trick is to look at the following expression, which is c to the rp, and you'll see in just a moment why it's so useful to consider this particular expression. C to the rp using exponent laws is equal to c to the r to the p. First we're going to substitute this in here, so we get b to the p, and then we're going to substitute this in here so that we get this is equal to x. And finally we're going to take this over here and substitute it in, so we get that this is equal to c to the q. Now we've got c to the rp over here, and we've got c to the q over here. Since they have the same base, and the base is positive, that is c, we can say that rp is equal to q. And indeed, that is what we wanted to prove. So that proves the identity that we can decompose log b of x in this way. What I want to do next is show you a few special cases of this identity which prove its usefulness. So the first one that I want to get into is called the reciprocal rule. And it says that for all b and c that are positive reals, it's true that log BC is equal to 1 over log CB. So basically we're switching the base and the argument to get that log BC is equal to the reciprocal of log CB. Let's try to prove that using our new identity, which is the change of base identity. We have that log BC can be decomposed as log CC over log CB, and it really boils down to computing the numerator, and since c to the power of 1 is equal to c, the numerator is just 1, and we get log CB as desired. The second identity that I want to derive from the change of base identity, I don't know if it has a name or not, but I'll show you what it says. It says that for all b and x in the positive reals, and for all real a, the following identity is true. Log, the base is b to the a, and the argument is x to the a. And what it says is that we can just get rid of the a's so that it's log b of x. This identity actually doesn't show up too much in literature, but it is useful, for example, in math contests. So it's worthwhile to be aware of it. So let's prove it. We have that log b to the a with argument x to the a is equal to log b x to the a over log b b to the a. And now we're going to use a particular rule, which is called the power rule. We have to prove it separately. I'm not going to do that here, but we can use it, and it has a separate proof. It says that log r s to the t is equal to t times log r s. If you have the time, I do recommend proving it on your own, but I'm just going to use it here. So we're going to apply it to the numerator, and we're also going to apply it to the denominator, so that we get a log bx over a log bb. The a's cancel out, and we get that log b of x over 1 is equal to this expression, which is just log bx as desired. Now there is one sticky point, which is the possibility that a is equal to 0. And if a were equal to 0, then we would have log 1, 1. And that's not actually a well-defined expression, because 1 to the power of anything is equal to 1. So this is not actually a well-defined expression. So we'll say that a is not equal to 0. So we'll exclude that possibility in order to avoid any confusion. There is one more identity that I want to derive for you based on the change of base identity. Again, I don't know if this one has a name, but it is useful. And it says that for all b and x in the positive reals, log 1 over b of x is equal to negative log b of x. Let's prove it. we're going to be using the fact that 1 over b is equal to b to the power of -1. That's by definition true. So the proof goes like this. Log 1 over b of x is equal to log b of x over log b of 1 over b. So we use the change of base identity here. And now it's a matter of computing the denominator, and that's where this comes in handy. It's true that b to the power of -1 is equal to 1 over b, so we get log b of x over -1 is equal to this expression, and that's simply negative log b of x, which is what we wanted to show. Okay, so let me do a summary for you about what we did today. We started by stating the logarithmic change of base identity, which is about decomposing a logarithm into two logarithms that have a different base. Then we proved it by changing all the logarithmic expressions into exponential expressions. And then we ended by proving three identities using the change of base identity, including the reciprocal rule, which is this one over here. Then there is this sort of exponential rule, although that's not an official name. It allows us to get rid of the similar exponents in the base and in the argument. And finally, we proved this identity over here, where we want to have a base that is the reciprocal of the original base, and that tacks on a negative sign. Okay, thank you for watching, and I'll see you next time.